Yeah, I was looking at this just before I came this morning. Apparently, it says Kentucky mine, but it's actually a reconstructed mine in the Sierras in California, a silver mine, I guess. And so this is just converting water, moving water into rotational energy, such as you need for generating electricity. Let's see if it starts up. How does it start up? I can't quite work out where the water comes from. Perhaps it comes from the right side of this, I guess. Yeah, the right side underneath. Can't work it out. But you know, it's the same as the air one that we showed on a desktop the other time. It's called a Pelton Wheel. And I don't know what they'd have been using rotational energy for then. They certainly weren't generating electricity in those days. They could have been using it with a cam to actually have a stamp, maybe to break up ore or something similar. Hey, Jacob. And so that's kind of curious. So, conservation of momentum at work. I don't know if there's a way to switch between these different tabs without going out. We've seen this one before as well. The jet lev. I thought I had some more interesting ones where they actually, I told you about it, where they actually go, they have 10 of them all doing kind of synchronized swimming type moves, not swimming obviously, but also not just staying above the surface, but also diving below it. So going down and up and like dolphins, I suppose, with multiple ones of these kind of synchronized, which is kind of cool. Maybe we'll look at that some other time. But again, conservation of momentum. You can see that actually it's a pretty big barge that comes behind you with this umbilical on it, which is quite large diameter, 4 inches or so, to get enough water in to be able to get you up off the water. And the controls, just like a motorbike, I guess, with a throttle on it. And I'm not sure whether you can change the flow rates in each jet with a throttle in each hand, or how it works. But it looks like you have pretty fine tuning if you can land on a deck like that. Mythbusters you saw, but we'll talk about that again today. So we'll continue talking about conservation of momentum. I'll try and summarize things and go through 3 examples. So a few equations to get to, but I'll try and make it as straightforward as possible. I looked at last year's class, and I think it's quite well presented to state things out, but then I would say that, of course. So that's the plan today. Sleeping giant, guillotine.
That is a lovely, lovely sound.
The valve has sheared clean off, and that's a very good sign. It looks like the cylinder flew straight and true, but did it have enough thrust to crack the wall?
Well, we know the answer, right? So it went through one block wall and tried to go through a second one. And I guess probably retarded a little bit by the fact it has friction on the bottom acting against it to slow it down. But certainly went through, yeah. Looks like a regular block, right? Looks kind of thin, actually. Oh, no. Yeah, blocks are hollow in the middle and have faces on both sides, cinder blocks. Yeah. If it's on the 5th floor of Dyke, you might end up with it in the top of someone's car, I guess, if it goes out through an outside wall, which it could do, I'm sure, based on... and so all the gold in California is alluvial gold. It's been eroded out of the mountains and deposited as alluvial bluffs in water. And then this alluvium, which is just loose soil, is then mined. And one of the easiest ways to mine it is using what's called a monitor, which is exactly what you're looking at. And I guess the interesting thing to look at the monitor is that its shape. It has these kind of interesting bends in it to try and reduce the amount of force that it has when it's sitting in the cradle. It has these right angle bends before it comes out of the nozzle. And that's so that you don't have to, you know, if you have a fireman's hose, there's a lot of force pushing you back with that. But by having these bends, it allows you to make it a bit more manageable in anchoring. And so obviously the power of this is just eroding, not very environmentally sensitive when this was done. And but basically the idea is just to be able to, instead of using a digger, use water power from higher up in the Sierras, because this would be alluvium, which is not super low down. I remember Grass Valley is one town, which is in the low Sierras, where you see these very steep, kind of cemented soil slopes, which are ex-alluvium. The rivers have perhaps gone lower, and they contain specks of gold at relatively low concentrations, but higher than zero. And so you gather a lot of this muck, you beneficiate it, you take the gold specks out of it by allowing it to gravity settle, because they're denser than the quartz around it. So either by panning or by using centrifugal separation or something. I guess that's it. So anyway, those are the kinds of things that we're thinking about today. So I'll get back to what I did mention for the people who are here as early birds. Today's the day for getting assignments in, projects, I guess. I think it's not a super hard deadline like our other assignments are, but oh, that's not it. Yeah, it is it. Okay, I thought I was further on. And so I think that's today. I'm sure that Shin will be in contact if you're late, if he doesn't get something from you. And I just need to find out where we are. A bit further than that. I guess the problem with this is it doesn't really have a go through the pages thing. To go just page by page, well, you can see that you've avoided most of these handwritten notes, because I've done handwritten notes in real time, and so I think it's conservation of mass. Maybe I'll cut this part out of the movie as well, since it's kind of downtime. Yeah, I thought I set it up to be, is this 7-1? All right, almost there. All right, so we went through this undershot weir example yesterday, or Monday rather. And so what I wanted to do today, if we get there, is to kind of recap what we're doing, put it in some kind of context, and then do 3 different examples. We already did one. We did the undershot weir yesterday, Monday. And I'm going to do the jetpack, the vane, and the decapitated cylinder. And the reason for this is that the jetpack is what we would call steady and non-deforming. I guess they're all non-deforming. The vane is moving. And it's a bit like the Pelton wheel, but on a linear momentum rather than rotational momentum. And the decapitated cylinder, which is ostensibly non-steady. So those are the 3 things we'll do. But first I wanted to kind of recap exactly where we are in terms of what we've done. And the 2 things that we've looked at are conservation of momentum and conservation of mass. And so just to reiterate those again with the diagrams we've had, I think you can't get too much of this. V1 and V2. The normal to the boundary and what this means. I think We know the expression is density times a rate of change of volume plus rate of density change times a volume plus these are all summations, mass rate of flow equals 0. And we also have conservation of momentum. Guess I should be consistent. And how will we write that? I guess we'll write it as sum of forces is equal to W plus VCS. So relative velocity times VCS times mass rate of flow, and I guess this is also a summation. And we should make the case that mass rate of flow is equal to density times velocity times area. And that's what goes in both here and in here. And so it's important to remember this. I guess the other figure that I should probably draw is our little boat, the fireboat. If you looked at the videos, you'd have seen this. That's not a bad boat, is it? Even if I say so myself. And if you have stuff squirting out of this, out of the hose at velocity W, and if you have the boat itself moving at some velocity I'll call VCS, then the sum of those two is what we call V static. Okay, that's important as well. I've drawn these too close. See how skillful I am? Oh, look at that. Not often I can do that first thing in the morning. So if we do conservation of mass, we've also talked about the sign convention. So a rate in goes in the opposite direction of the unit normal. And so for conservation of mass, this is a negative value, and this is positive. Positive out, negative in. So this is for mass. And for momentum, we're only talking about this first term here. And so these terms are, this is V static. So you remember from this expression here that V static is equal to the control surface plus the squirting velocity, the velocity out of the control volume. And so each of these are in terms of, written in terms of this relative to the control volume velocity. So this term here is V static. And of course, the reason for this is that the inertial reference frame, when we accelerate something, we want to be static on the Earth. The Earth is actually moving at 1,000 miles an hour. It has circumference of 24,000 miles, and it goes one rotation in a day. So it's 1,000 miles an hour that we're moving at right now, but we're all moving at that. We're not accelerating, but we're moving at it. So everything is in our static reference frame. And the importance of using these, so that's the reason why this is the rate of flow out of the control volume plus the velocity that control surface is moving. So this would be the velocity of the ship. This would be the velocity out of the hose. And together, the static observer would see the water moving at this total velocity because the ship's moving at 1 meter a second, squirting at 1 meter a second. If it's squirting backwards at 1 meter a second, it would see no velocity, right? Because they would cancel out. This is the vector sum. So that's important. It's important that also if you think that you're sitting inside this control volume, then you're interested in the W, the rate at which it comes in, and the rate at which it goes out. So if it goes out through the top, that's a steady state condition. So it's the rate it comes across the boundary of this that's important. So that's why we have this W in here. And I guess I didn't get round to the second one. The second one I was going to say is that this V static is a Cartesian. After René Descartes, right? Cartesian. And so this is in the X and Y directions, or X and Z directions. So this is positive X, this is positive Z upwards. So in terms of this velocity here, this would be positive because it's acting in the positive X direction, and this is positive here. So that's all you need to know about these two things. And so we can use these now to be able to solve these three problems. So jetpack first, and then a vane, and then the decapitated cylinder. Okay? All right, so that's it. So I'll draw a line under this. That's our key. And of course, if it's steady state, then these terms here, there's no change in volume with time. There's no change in density with time. Remember, we explained these as change in volume with time is filling up a bucket where the control volume maybe increases. Change in density with time is pumping up a tire where the density increases but the volume doesn't substantially increase. If these are both zero, then we only have to worry about this term here. And so the first thing we'll look at then is our guy or gal on the jetpack. And the jetpack has an umbilical which comes in and water that squirts out. And so we can make that into just a very simple control volume that I'll draw here, and then we'll just go through it piece by piece. So I'm really drawing a control volume around this. And so this is our control volume. Do it a bit more simply. I'll try and use different colors for the different things. For the water in through the umbilical. What have I called it? V1 and V2. So this is V1 and A1. I'm never quite sure whether you prefer me to have this all pre-written so we can zip through it at warp speed. My guess is that perhaps you don't prefer that. But what else? I will use mg, so we don't confuse it with w for this velocity. So it's the mass of a person times gravity, 100 kilograms times gravity. And I guess if we're cutting this off, we also have the pressures acting into the system. Bless you. So it's P1 and this is P2. And then we have to be able to deal with that in some way. And so our equation is going back to this. What do we know? VCS is equal to 0. It's not moving, static, it's just levitating. And so we can write this expression here as sum of forces in Z is equal to the sum of W plus CS, just include both perhaps, times mass flow rate. And we can start figuring out what each of these terms are. So in Z we have minus mg, we have plus P1 A1, sorry, P2 A2. We have a component of the force here. It's acting in the x direction only, so there's no component in z. We know that when the fluid comes out of here, as soon as it comes out, if we look at the pressures acting horizontally, they're 0, right? Because it's atmospheric. And so this can be taken as 0. And this is equal to the velocity, W. So this is going to be equal to the velocity 2 times the mass flow rate. The mass flow rate is going to be, what do we call it? W rho A. Well, it's not sum because it's summed right here, I guess. So this is V2 times V2 rho A2. And we have to figure out what the directions are. So this here, this term here is the mass flow rate. Mass flow rate out is positive, right? So this is a positive goes here. And V2 is in the, if we draw a coordinate direction, a proper coordinate direction that takes care of gravity. V2 is negative. And so we end up with an expression, if you just simplify it, is that mg is negative on both sides, is equal to V2 squared, this is negative, times rho A. So the mass that we can hold is equal to V2 squared rho A divided by G. That's it. Or if we wanted to calculate the velocity we had to get to be able to lift that mass, I guess it would be V2 squared is equal to mass times gravity over density times A. Take the square root of both sides, obviously, and get rid of this. That's it. So we have two useful things. We can figure out what velocity we have for a mass, or what velocity we have for a mass, or for a given velocity, you can figure out what the mass is that we can lift. That's it. So we don't have to worry about this force here because it's orthogonal, so it doesn't come into this equation. And so we don't resolve anything else. That's it. Okay. So that's straightforward because it's static. We can then maybe, everyone okay with that? So we can then maybe look at a vein, a static horizontal vein. So the second one is a vein. All right, so there's an example in the book. It's a bit more complicated, but this is the basic idea. You have something sitting on a surface. It's on rollers. Yeah, it's supplied by V static by a hose, and that V static must comprise the velocity of the control surface plus the velocity of the water relative to it, right? So if you have a hose that has 10 miles an hour velocity coming out of it, that's V static, you're standing on the ground. W is the velocity that it would see in this vein. And so the geometry that I want to emulate is that this jet of water comes in, goes up through this control volume. So what do I call it? I call it W1 in the x direction. I suppose I should draw some, I'm trying to be reasonably careful with this, so I actually give you something that's useful. So x and z, again, coordinates. And so this would be W2, but in the z direction. And I suppose we could also put a force on this, which I'll call a reaction in x, I think. Yeah. And I suppose I could also, in the same light of this, we could think of this as being this velocity of the control surface. So VCS is the velocity at this. So the idea is you hit this vane and it moves at some speed. And the question is what speed, what force do you have to put on it to be able to restrain it? And so that's the question that we'd like to answer. And so this will have an area A2, and this would have an area A1. And what else do we need to know? So the expression that we're going to use is going to be equal to, so sum of forces in the x direction, probably, because we're interested in what it does in x, is equal to W plus velocity CS multiplied by mass flow rate. So there's some things that we can perhaps do with that. What else? What do we know? Well, we could also write this as sum of forces in the x direction are equal to the sum of forces W. I guess these would be x. I guess I put them up at the top so it doesn't interfere. So this would be x times mass flow rate plus, I'm just breaking this equation apart. So if we are steady state, then we know that the sum of the mass flow rates are equal to 0, right? So if you're sitting on this and it's steady state, by definition, the same volume rate of fluid is coming in that's going out because it's not accumulating. And therefore, the mass flow rates have to sum to 0. And so this is the case. So we immediately know that if you multiply this by a constant, for instance, if you multiply this by the velocity of this vane, which is constant, then this term together has to equal 0. Right? That's the first observation. And so that means we get rid of this second term. So what we're left with then is being able to figure out exactly what this is. And so now we can break it up and we can sum these components. So the forces is minus Rx. I guess we don't need a, that's the only force we have acting. And we have a velocity which is Wx1 times the mass flow rate. So this is the mass flow rate is going to be rho times W1x times area 1, right? This term here. And what else do we have acting in the x direction? I guess we have plus W2x times rho W2z times A2. This is x. I meant to put x there. So this is Cartesian. This is the velocity of flow here in this direction. And of course, there is none. W2x would look like this. There's no component. And so we get rid of this is equal to 0. So we didn't need to do that. There's no component. And so this is our expression. We know from this that we could write V static. Well, we should do the sign convention as well now, right? So what do we do in terms of signs? The sign acting on the mass flow rate is in. So in means that it is negative. So there's a negative sign here. And it's also in the positive direction, so this is positive. So there's a negative on the mass rate of flow, and there's a positive on the Cartesian velocity of this coming in. It's in the x direction. And so that's the final expression that we have. So we can also, so we have, so it's negative, so we have Rx is equal to W1x all squared rho A1. That's it. And what we can do now to make it a bit more interesting is that we can also write this vector sum as V static is equal to VCS plus W. We could rearrange it as W being equal to V static minus VCS. Bit long-winded, but that's a useful thing to do. And so now, what I want to do is substitute this. And so we have, this is almost the punchline, is V static in the x direction minus V control surface squared rho A1. So we typically know what the velocity is coming out of our hose because that we're standing holding it. So that would be what we would know. So there are two conditions. Or two end-member conditions. Either we can hold the vane static and see what the force is that we have to hold it at, or we can let the vane run with no force on it and see what the velocity is. And so the first case is Rx equals 0. If Rx equals 0, the only way that that can be is if V static equals V CS. So in other words, the velocity of the vane moves. It's exactly the same velocity that you're pumping water at. And so you're thinking it's moving just at exactly the same rate as the front of your bead of water out of your hose. Makes sense. The other condition is that VCS is equal to 0. If VCS is equal to 0, then Rx is a maximum, and it's equal to V static squared times the density of water, if it's water, times the cross-sectional area, A1. So that's it. So that's about as simply as I can make it. There's always one of these questions on the test. It's just so knowing how to do it is important. You'll see them recur. There's no mystery in that. So that's it. So the two end-member conditions are the ones that perhaps we're interested in, and they make sense. If you don't hold it back and it's frictionless, then the velocity it moves at is exactly the velocity that you're pumping water at. That's kind of the end-member behavior. And if you try holding it in place, then by definition it has 0 velocity, and that's the maximum force that you have to apply to be able to hold it in place. And so the other interesting feature of that, I guess, is that you can look at power, not rower. So we looked at this Pelton wheel, which is kind of a version of this, right? A Pelton wheel just has a rotational arm on it, so it's rotating about a center, water squirting at the wheel, it's going round, it brings the next one in, etc. And so it's kind of like a Pelton wheel, but on a linear system. And so we can look at power. Power is defined as the velocity of the control surface multiplied by the force, which is the reaction. And so what we could do with this calculation we've just done is we could plot force versus velocity of the control surface. So we have these two conditions. When the reaction force is 0, then the velocity is a maximum, and it's equal to the static velocity. And so this, we would have one point would be this. This would be this. The other condition is if we are holding it still, the reaction is a maximum, and that would be this point here, which is our point 2. And I don't know that they're necessarily joined by a straight line, but they're joined by something. And so the interesting thing is if you draw from this power out of this, which is equal to the reaction times the velocity of the control surface. Here we have a big reaction, but the velocity of the control surface is 0. And so the power at this point, 2, would be 0. Likewise here, we have a velocity which is big, but the reaction which is 0. So this also has 0 power. And at some intermediate spot, we have a reaction which is half of the max, and we have a velocity which is half of the VCS, roughly. And so these are definitely non-zero. And so this curve would look something like this. So you can hold it still, and you get no power out of it because power requires the product of these two. It has to be moving, and it has to be doing work while it moves. And so you can look at it'd be like trying to generate electricity from a buoy. If a buoy is anchored in the water and the waves are lifting it up and down, if it's anchored so it can't go up and down, you've got lots of force on that buoy. The buoyant force as the waves go past it, but it's not moving, so there's no energy generated. If you want to generate electricity, you've got to allow it to move partly with the thing, but still keep a tension in the cable so that you're sitting somewhere within here. So it's kind of interesting. So yeah, so I think that's just a curiosity as much as anything. So anyway, so that's kind of the deal here. And so look at it. I try to make it as simple as possible. It's a bit complicated, but you realize that we're just using exactly the expressions that we talked about, including this term written as this, to be able to do the calculations. Okay? Questions? No? Okay. I'm such a great professor. Everything's so crystal clear. Good. Yeah, go. Hit me.
For the when we said that VCS times mass flow rate was equal to 0 there.
Yeah. Why?
I mean, I know that you made that assumption, or that because it's steady and the mass flow rate is equal to 0. But why are we able to cancel out the like the velocity of the control surface and not?
Because it, yeah. There's a very subtle difference. If you, I presume I talked about it in the exam week 6. We have two things: velocity of control volume, and the velocity of control surface. Control volume, if you remember, we talked about 3 conditions: kind of a static pipe with fluids moving through it. We had a jet engine which was rigid, non-deforming, but moving. And we also had the whoopee cushion or the balloon, which is a moving and deforming. So this is the velocity of the control volume. By definition, the volume, since it's deforming, any place you look on this would have a different velocity of the control surface, right? This rigid thing, as it's translated, would not. the velocity of the control surface here is the same as the velocity of the control surface here, and is the velocity of the control surface here. They're all moving at the same velocity by definition. And so VCS, by definition, is a single number for the body, and therefore if you multiply a single number by something that sums to zero, so if sum to zero, if it's, yeah, so you get it. So it's just a single number multiplied by something that sums to zero, and so any number multiplied by something that sums to zero, you can test it out for any things you choose. So if you have 1 plus 2 minus 3 are these components of the mass flow rates. If you multiply each of these in turn by 2, you still get 0.
Yeah.
That's it.
Okay. Maybe I just don't understand what the water jet velocity is then, because isn't that steady number?
This water jet velocity is this speed that's coming out of the hose.
Mm-hmm.
This is the speed that it's coming into this control volume. If this control volume is static, then W would be equal to the full static one because VCS would be 0. And if this control surface was moving at the static velocity, then W would be 0. It would have come in the first time, but no more would ever come in because it was moving at it. Okay? Good questions. It's important to get it. It's not straightforward. I realize this kind of analysis. Okay? So think about it. And go through the videos at 10 speed or 2 speed or half speed, depending on what you want to do. So we said we'd do 3 examples. So true to my word, jetpack we've done, the vane we've done, which is kind of a Pelton wheel. Friday we'll do rotational stuff, true, but you get the idea that if the lever arm is long enough, then it really is a linear system. If the lever arm is short, then you have to take account for the rotation. And the final one is my favorite, the sleeping giant. And so I get to draw one of these. Gas cylinder. And its claim to frame. So the 2 other things were static, first of all, jet lev. Moving, obviously, the vane was what we're doing. And now this is moving but non-steady. And we kind of said we weren't doing non-steady circumstances. We threw away one of the terms in our Reynolds transport theorem because we're not accumulating momentum in the system. So we're still not doing that. But this system is non-steady. So again, the cartoon. I'll draw it just as a block because it's easy to do that way. With a little cap on it. And 2 locations. Location 1, where we have P1, V1, Z1, and location 2, where I'll draw it like this as V2, and Z2, P2, and in this case A2 matters. Can't remember if I used these other colors here. This is the pressure that's acting. I guess I'll label this in a minute. So this is P2, and the blue stuff is V2. Yeah, okay. Actually, don't. Just minor cosmetics, but you get the idea. And so I guess we'd want to solve that. So let's do our coordinate system again. X and Z. Let's have our control surface velocity, VCS. And let's write Bernoulli. We write Bernoulli because we want to know what V2 is. So P1 over gamma plus Z1 plus V1 squared over 2G. We've seen this, you know, equals to P2 plus Z2 plus V2 squared over 2G, not Y. What do we know? Well, P2 is outside, so for the same reasons as we said before, P2 is 0. I'm going to use red so you can see it. If we take a horizontal datum through here, given by my red line, which I'll remove, and we know that Z1 and Z2 drop out. They're not 0, but they cancel out. We know that P1 is probably big, but we know that V1's not moving when it's static. So assume it's static, and we're just trying to calculate this, and so we can solve for this. So P1 for gas cylinder, I don't know, a highly pressured gas cylinder is 100 MPa. I know because we've tried to purchase some of them to run our experiments. So the density of gas is, well, it's not equal to 1 kilogram per meter cubed at these kinds of pressures, but you could use the ideal gas equation to get it if you wanted to, right? P is equal to rho RT. And so if you know what pressure is and gas constants and temperature, you know what density is. So bottom line is we can calculate what V2. So that's the moderately straightforward part. So now we can put a control volume around our system. I guess I'm going to do it so it just comes through here. And we can look at our relationship. And we're interested mainly in the x direction. Sum of forces in the x direction are equal to the sum of the out of the container velocity plus the velocity of the control surface multiplied by the mass flow rate. The mass flow rate is going to be V2 times A2 times density. Yeah, okay. And so we can look at each of these components. So V2, of course, is going to be equal to W2, right? Yeah, okay, so it's straightforward. And so we can merely write this as the force that we're going to have to apply. I guess we call it Rx again, right? The reaction we have to apply to hold it in place. So Rx is equal to, and we only have one jet coming out of here. So this is W in the x direction, W2 in the x direction, plus velocity of the control surface times W2 in the x direction times A2 times rho. Yeah, so. And we can do the same hijinks as before. And so two conditions. If we fix it, then by definition, what order did we do it before? We did Rx equals 0. So, so if the force that we apply is 0, then the only way we can get the right-hand side to be 0 is if then W2x has to equal minus VCS. Okay, we didn't do our games, did we? We didn't do our games here. So we didn't do, what we didn't put in was the right pluses or minuses. So Rx is in the positive direction. So this is definitely positive. W2 is out of the volume. This is our unit normal. I can't draw it properly. There's too much stuff here. Well, you know, our unit normal is this. So out for this is positive. So this is multiplying by a positive value. And this is also in the positive direction. W2 is out of here. This is what V2 is. And so this is also positive. So it turns out that these are all positive. And so the only way we can get it to move is that 0 is if VCS is in the opposite direction as W2, which is not right, is it? So what have I done wrong? This is only going to be 0 if W2 is equal to minus CS, and of course it's going to, oh yeah, okay, fine. So W2 is positive, of course it's right. VCS is in the negative direction. It's going to move in this direction, which is minus. So it's going to push this way, and it's going to move to the right, to the left. So yes, my brain burped there. So the other option is that velocity of the control surface is equal to 0. And so if this is equal to 0, then that only occurs when the reaction is a maximum and the reaction is equal to W2 in the x direction times W2 in the x direction times area 2 times the density of the fluid. And the same applies, right? These are the end-member behaviors. This is positive, W squared, and so this is positive force. So the force you have to apply to keep this static is in the positive x direction, and it's just stopping it from moving. That's it. So that's about as simply as I can make these 3 cases. So they're a good reference, I think, for the things. They turn up often in the things, and they almost, yeah, there'll be something like this. But something that requires that you have this kind of feel for it, of exactly the fact that these 2 end-member behaviors are useful in your own mind, of just anchoring the fact that here, just like in the case of the vane, in the steady state, this thing is moving at exactly the same velocity as this is coming out of the cylinder. It can't move any faster because static, I guess the dynamics tell us that it can't move faster, but it'll move exactly at the velocity of this water jet. And so we can calculate these 2 end-member conditions. If we wanted to, again, to calculate the power exerted by this, it would be the same as this. The power when it's moving but not restrained is 0. The power when it's restrained by a large force and not moving is also 0. And in the intermediate portions, it expends some power, but at these individual locations, it doesn't. So that's it. So that's it. So I don't know, questions, if any? I think it's important in doing these. Still ask questions if you were going to. I didn't mean to cut you off. It's important just to come down to the fact that these are the expressions that we should be using. So this is the summation for the conservation of mass. This has to be relative to the moving volume. So think of yourself as sitting in a bucket. It matters what the rate, the velocity into the bucket is relative to you and out of the bucket. So it has to be relative to the contours of the bucket that stuff is going in. But it turns out that's also important when that definition of conservation of mass applies in the conservation of momentum equation, but the inertial frame of static, us sitting on the Earth, ostensibly not moving, even though we're moving at 1,000 miles an hour, is the inertial frame that we use. You remember that we said that F equals d dt mv. This is the same as F equals ma. This is the substantial derivative. This means it matters the reference frame. The reference frame is our static reference frame that we're using. And we use that to do an example with a sonde going up a borehole and sampling different temperatures. And as we go in, we get the geothermal gradient. So it matters as temperature changes with location. And it also matters that temperature changes with time. Too much information probably. But to make the point here that this W plus CS is because the reference frame that Newton's second law uses is the static reference frame that me sitting here is not moving. If I move, then I need to use some energy to change the momentum from 0 to actually moving across the room. So this has to be what we use. And this is just one equation which we can resolve for. And if we needed to resolve in the other directions, we could also do, well, relevant to this, we could do this. This would be easy for this one, right? Because in the moving one, the velocity of our control surface in the z direction, it's not going up at all. It's just translating horizontally. So this would be 0. And so it would just, if we wanted to know, for instance, the force that was acting downwards on this, then that force would be something like, what would it be? So Fz would be equal to plus our, we'd have to be careful with our, so Fz is positive because it's acting in the positive z direction. W2 for the calculation here is out of the volume, so this would be positive. And Wz is in the positive z direction, so this would also be positive. So that expression would just be Fz equals Wz as that. So you can resolve in different directions. And so W2 is positive. If it's non-zero, I guess if it's non-zero, then it means it's coming out of here. You could imagine that it's pushing the vane down. And so the reaction against it in the F direction would be positive. So this would be positive if this is positive coming out of the system. If, for instance, the vane was moving at exactly the same speed as the jet, so that the jet was just keeping up, the first drop of the jet was keeping up with the front as it moved, then by definition, nothing could be coming out of the top. It'd be coming out of the top at zero velocity. And so the force then, if this is zero, the force acting downwards, apart from its self-weight, the force added by the jet would be zero also. That kind of makes sense as well. Useful thing to think about. Yeah, okay. So, no questions? Silence? Frightened? I don't know. So I've tried to make it as clear as possible. These are the expressions you should be using that we identified in the top part. If you use those expressions, you'll never go wrong. You don't have to worry about Reynolds transport theorem. You just have to worry about this. You don't have to worry about it. You just have to be cognizant of this stuff here and physically what it means. A bit complicated, but it's a kind of bookkeeping. It's also a bit of thinking about what's going on. You have to draw free body diagrams or control volumes around your stuff and look at the pressures that are acting. You know, these pressures are, if you cut your control volume, this pressure is the pressure that's acting on the outside. This is the velocity that's flowing from the outside into your control volume, etc. So you just need to get these right. This is in atmosphere, so it's zero. This would not be equal to zero, right? This is the pressure that's coming in from the umbilical, and so it comes under pressure, and that's the reason it squirts out. The reason we don't care about it is because it doesn't have a component that acts in the z direction. So then when we resolve vertically, we get that. If we resolved horizontally, it would have a component that's attached to it. And that's it. So bring your questions on Friday. If you're too shy to ask them now, I guess we're 5 minutes over. No one's yet come in. And we'll take care of it. Great. Have a day. Great day. Looks like a great day compared to yesterday. Perhaps even dry.